This lecture covers the beginning of section 3.1, limits. Limits are a fundamental concept in Calculus 1, perhaps the fundamental concept in really all of calculus. We're going to learn what a limit is, why we care to find one, and maybe not really techniques for finding them, but maybe just how to brute force use a graphic device to find it. Let's consider problem 1. Suppose at a time t we have a population given by this function right here. And if this is weird notation, then you can just consider it p of t, like that. What is the instantaneous rate of change of the population at time t equals 3? How quickly is the population increasing at exactly that moment? Okay, just keep that in mind. Maybe think about what I might mean by instantaneous rate of change. Let me ask another problem. Problem 2. What is the slope of the line tangent to the curve f of t equals t squared plus 7t minus 6 equals 3? If this is confusing, you can just call it p of t again. That's fine. But this is something maybe a little bit more approachable because, I guess I should call this the t-axis, because we're used to graphing things, right? And we should be able to see that this is a parabola, right? And it looks something like this. And at t equals 3, I mean, this is not exactly drawn to scale, but we're roughly right here. Okay? And so it makes sense to talk about the tangent line, right? Remember, the tangent line is the line that grazes the curve at exactly one point. Right there. There we are. Okay? So the question is, what slope is that line? Right? This is the graph y equals f of t, and that's some tangent line, okay? Well, it turns out that these problems are actually the same. I asked the same problem, and they have the same answer, but I just asked them in completely different ways. Problem 1 was an applied concept. Problem 2 was a graphical analytic geometry question. And yet they have the same answer because they really are asking the same thing. And over the next few weeks, we're going to learn why. Not to keep you in suspense, by the way, the answer is going to be this guy. I guess I'll call it P, right? Alright, that's our answer. If that's a little complicated, we could use the alternate notation. It looks a little bit like this. Alright, obviously, right? No, I'm just kidding. You probably have no idea what I'm talking about. But just so you know, the answer is, in fact, it's 16. It is 13 units of population per unit of time. Right. Now, how did I get this? Well, check back in a couple of weeks. For right now, let's figure out what the heck this even means. Okay? So in order to do any of this stuff, we have to define limits. So first off, we have this notation. I guess I'll say this guy. Limit as x approaches a. Just to be crystal clear, that is an arrow. X approaches a, f of x equals L. What is going on here? This right here reads L is the limit as x approaches a of f of x. Or you could say as x approaches a, f of x approaches L. Now the technical definition is a little more complicated than that, but we won't get into that right now. Instead, I just want to introduce this notion of a limit, right? This idea that if we have let's go back to the x-axis instead of the t-axis. If we have some kind of a function here, and there's a point of interest or a value of interest a, we're interested in what happens if this is like y equals f of x, for example. And maybe we're at L right here. We're interested in what happens as x approaches a, both when x is a little bit bigger and when x is a little bit smaller. And before we can even begin to address this kind of problem, I want to get a little bit more into the weeds with the definitions. We can actually define a left hand and a right hand limit. Now, a left hand limit and right hand limit are really the same thing. I would just tack on the phrase from the left. In fact, let me just even write that right here and actually change this to red, right? So the limit as x approaches a, and then I put that minus sign right there. That means from the left of f of x equals L. That means L is the limit as x approaches a from the left of f of x. Now, you might imagine there is a right-hand component as well, right? If I write a plus instead of a minus, I get that. And that means L is the limit as x approaches a from the right of f of x. Okay? So let me just give you an example of what's going on here. If we have an axis, right? X and a y-axis. Suppose I have some big, scary function, blah, blah, blah. Maybe I'll create a hole right here, do one of these guys. This guy. Maybe I'll go like this, that, and we'll go here. Okay? And suppose this is my function y equals f of x. So there's the question, what do we mean by left and right hand limits? Well, I'm going to consider the points of interest, or the x values of interest, a, b, c, I guess I'll call this d, this point right here. I'll call this, I'll just call this point S. Okay. So let's take a look. I guess I'll also consider a couple of y values as well. Call this guy L, call this guy M. Maybe I'll call this guy N. Maybe I'll put this up a little bit more right here. There we go. Okay. So now let's take a look at what we've got here. When I talk about the left-hand limit as x approaches, let's say, a from the left, I'm saying what happens on the graph as we get closer and closer to a from the left. Right? So consider this point right here that corresponds to x equals, right? This is f of a in this case, right? But what happens to the graph as we get closer and closer to a? What does y do? What about as we approach a from the right, right? A little bit bigger than a. What happens to the graph, right? Well, in this case, here maybe I'll call this guy O, right? In this case, the limit as x approaches a from the left of f of x equals O, right? Because the graph gets closer and closer to that y value, O. Also, the limit as x approaches a from the right of f of x also equals O, because again, as we get closer and closer from the right, we get closer and closer to this y value. Okay. Now, let's see what happens for other values. What about as x approaches b from the left? Well, actually, let's not worry about the right now. As x approaches b from the left, it looks like we're approaching this value L, right? So we would say the limit as x approaches b from the left of f of x, there is a minus sign right there, is going to equal L. But what happens as x approaches b from the right? Well, I don't think we're going to get L again, right? Because now we're going this way. And so we're getting closer and closer to this point, which is M. So note that in this case, the left and right-hand limits were different. Okay? So let's take let's just keep doing this, right? Consider C. Well, in this case, note that whether x approaches from the left or the right, the graph does seem to be approaching the same y value. And that's going to be n. Okay? So I'm going to write here the limit as x approaches c, well, that's an arrow, from the left of f of x equals n. And also the limit as x approaches c from the right of f of x equals n. It doesn't matter that f of c does not equal n. It doesn't matter. We're not talking about f of c. We're talking about what happens as x gets arbitrarily close to c without actually getting there. And what happens is f of x gets closer and closer to the y value n. Now, what is happening over here? This at D, or I should say near D, because at D, f is not even defined. Well, it seems in this case that as x approaches D of f of x, we are getting infinity, right? Which is a nice way of saying the function increases without bound. This right here is called a vertical asymptote. Okay. Oh, sorry, this is as x approaches D from the left. But note that it's also the same as x approaches D from the right. Also positive infinity, right? Because it's also increasing without bound, right? Whether we're going from the left or from the right, that's what we're doing. And last but not least, let's take a look at s. What happens as x approaches s from the left? Well, the limit as x approaches s from the left of f of x is going to equal, oh, I think I tried to, kind of in the middle. Let's say that it roughly equals L, right? Don't want to get a third point in there, okay? And then meanwhile, the limit as x approaches s from the right of f of x equals, and that's going to be n. Right? So this is sort of an informal, but I hope intuitive introduction to left and right-hand limits. Okay, now we can skip this activity for right now. And let's just skip to the formal definition of a limit. Let's skip to our definition of a limit. We say that the limit as x approaches a of f of x equals L, right? Notice I didn't put a plus or a minus in front of the a, right? If the left-hand limit equals the right-hand limit, and they both exist. They both equal some value L. Otherwise, we say the limit as x approaches a of f of x does not exist. Okay? Now, let's do one example. Maybe, let's see. Yeah, let's do this example right here. So if we go ahead, now you can go to the website desmos.com, or you could download the Desmos app. Either is totally fine. So, one sec, I'm going to turn on my keyboard, and I'm going to write f of x. Oh, let's see if it starts typing. well, there we go, f of x equals 5x to the fourth There we go. And notice I'm just typing this in. Of course, you could do this on a calculator. I just think it's nicer on Desmos. All right, and we're interested in finding the limit as x approaches -1 from the left and from the right. Okay? So let's see what's going on. So one way that we can do this, kind of the only way, we don't really know any techniques right now, but we can just plug in numbers close to -1. So if we plug in, let's say, -2, we get -8. Okay? That's not very close to -1 in the grand scheme of things. So what if we get a bit closer? That's a little bit closer. Oh, okay. Let's maybe get a little closer. See what happens. Okay, now we're getting a little bit closer, I guess. We've got... Make sure I entered that function incorrectly. I sure did. Yeah, I did. Yeah, okay. Okay, so anyway, we get 4.54. Okay, and then what if we get really, really close? It looks like we're honing in on something. Maybe I go even a little bit more than my chart was saying. -1.001. Okay. So, okay, it seems like maybe we're getting closer to 3. But what about from the right? Maybe we could skip the 0 and -0.5. Let's look at just the -0.9, right? Okay. What if we have f of -0.99? Okay. What if we go one more and we do -0.999? And we do f of -0.999. We get 2.99. Right? So, just looking at this, it does seem to be the case that we are approaching a number from the left and we are approaching a number from the right. Right? Actually, let me go back to Desmos 1 second, just show you what we're talking about. We're looking at -1 right over here. Let me just sort of hone in on this part right here. Oh, I hope I pressed copy. There we go. Okay. There you go. So what happens? Well, as x approaches -1, from the left, kind of looks like f of x is approaching 3. And as it's approaching -1 from the right, that also kind of looks like we're approaching 3. So it looks like the limit as x approaches -1 of f of x equals 3. Okay? And in fact, it does. Now, one thing you might look at in this graph, you might say, well, wait a minute. That looks like a pretty, I don't know, that looks like a pretty smooth curve right there. Why don't we just plug in -1? And that's actually what we're going to do, right? To find the exact left or right limits, we can just plug in x equals -1, and I'll write in parentheses, if legal. And really what I mean by this is, if we're not dividing by 0. right? So for example, when would it not be allowed? Well, let's consider example 6, right? Suppose we have this function. Determine the limit as x approaches 1 from the left or 1 from the right. Well, I could say, well, why don't I just plug in 1? Well, what happens if I plug in 1? I would get 1 squared plus 5 over 1 squared minus 1, which equals 6 over 0. We're not allowed to divide by 0. Okay, so maybe we need to be a little more careful. Let's go back to our graph and see what's happening here. So let's take this graph away, and let's instead consider g of x equals x squared plus 5, I think it was, divided by x squared minus 1. I think I got that right. Yeah, I got that right. All right, and so now let's see what's happening. As we're approaching -1, seem to have a little bit of an issue here, right? Right, because notice that g of, or sorry, was it g of -1 or g of, g of 1, sorry. As we're approaching 1, we seem to have a problem, right? G of 1 is undefined. Okay. But let's see what happens as we get close to 1. Oh, there it is. Okay, there's the rest of g of x. What about g of 0.99999? Looks like we're getting bigger and bigger. Okay. What about g of 1.0001? Right, and if I make the zeros more and more, you see how we're just diverging. So it seems to me like the limit as x approaches 1 from the left is going to be -infinity, and from the right is going to be positive infinity. So the limit as x approaches 1 of this guy does not exist. And we'll stop there.